All right. Hello again, everybody. I'm recording this again from my house, my home podcast studio. So last week, we looked at hash functions, not just for the fun of it, but because we wanted to build a hash table. Remember that a hash table is something like a generalized array, right? It's an array where we can use things like strings or other data structures as the sort of indexes. So here we're going to use strings as the keys and ints as the values, but you could theoretically plug in any two types for those things. So our hash table is going to support these operations here. So we're going to have like a size function that'll tell us the number of entries in the table. And unlike an array, right, the size can change. It can grow and shrink as we add and remove things here. Then we'll have an insert function that lets us insert a key value pair into the table here. We're associating the key with the value like that, so that later on, if we look up that particular key, we get back the value. If the key doesn't exist, then we'll create a new entry. Otherwise, we'll update the value of the key that's already there. We have a function that can check to see if a key exists, right? Because before we can look it up, we have to know that it's already there. And then we have a function that can look up a key and return the value associated with it there. So the goal is for these to run in O of n time in the length of the key, right? So they have to loop over the characters in the string, but we want them to run in O of 1 time in the size of the table. So it doesn't matter how many things you've inserted into the table, inserting things, checking if things exist and looking them up shouldn't get slower as you put more and more stuff into the table. That's our goal here. So our class is going to look something like this. We've got, of course, our public functions over there, the ones we just talked about. Under the hood, we have this structure for a table entry. And all that is just the key and the value sort of paired up with each other here. And then here's how we're actually storing this in the background here. So we have an array of pointers to these entries. The empty curly braces over here means that every element of this array is going to get initialized to L pointer. And the size of the array, that is our M, right? That's the value that our hash function is. So our hash function here is spitting out ints of 0 to m minus 1, such that we can use them as index into the array there like that. So this is the sort of skeleton that we're going to be working with here. Right. So like we were dealing with an array of entry pointers, not an array of entries, but an array of entry pointers here. So our hash table is sparse, right? Like not every element of the array is in use. So we need a way to mark which ones we're using and which ones we're not using. So the easiest way is we'll just mark the ones we're not using with null pointer. And then the actual entries that we are using are like dynamically allocated. Like we'll create them using new like that. So that's why we filled the whole thing with null pointers to begin with, is because that way we're saying like, okay, at the beginning, none of the entries are in use. And then as we create them, we'll sort of fill up the table there. Now, remember that collisions are two different strings that hash to the same value, and they're not a bug. They're always like a possibility of what we're doing. So in order to detect collisions, we have to store not just the values, but also the keys. So that's why our structure has both key and the value in it there like that. The size of the array is m, right? And our hash function returns 0 and m minus 1, such that we can use them as array indexes. So the main function we're going to look at is our insert function. The exists and lookup are sort of pretty similar, right? But mostly we're interested in how insert here is going to work here. So insert is given a key and a value, and its job is to sort of store the association between the key and the value in the table there like that. What we do is we hash the key, and then that gives us h, which again is in the range of 0 to m minus 1. So the first thing we do is we check that table entry there. If that table entry is a null pointer, then that means that this particular key has not been seen before. We haven't seen this key before, so we just create a new entry and store the key and the value in it. So like we've never seen this key before, so we're going to create a new entry and be like, okay, this key is associated with this value. On the other hand, if the table entry is not a null pointer, we can look at the key inside of this table entry. If it is a match for the key that we're given up here, then that means the entry already exists and we just want to update the value. We just change the value in the existing entry to the new value that we're given. Otherwise, that means that there is already an entry in the table, but the keys do not match. So that means we have a collision. So we'll have to figure out sort of like how to handle that there. Basically, those are the kind of three cases that we can sort of have in here. And lookuping and exists kind of follow a similar pattern, right? Lookup is doing this, except that instead of creating the entry, returning the value inside of the entry. And exists is literally just a return true or return false, depending on whether or not we find the entry. Let's consider what we need to do in the case of a collision. So again, collisions, they're not a bug, right? They're inevitable, right? There's always going to be more strings than whatever M we pick there. Our hash table needs to be able to deal with collisions. And there's sort of two general collision handling strategies. The one is called chaining, and it just means that we make our entries into linked lists. So all the things that hash to a particular index get stored in a linked list. And the other option is called open address. So in open addressing, the sort of way you think of it is if the index we want is taken up by a different key, we just look somewhere else. We pick a different index and then we look there. Of course, that one might be taken up by something, so then maybe we have to pick a third index and look there. So there's a kind of like a loop involved in it. Now, before we look at either of those two methods here, let's talk about something called the load factor. So the load factor, this is the Greek letter alpha here. It looks kind of that, right? But in this font, it looks like the letter A. And it's a measurement of how full the table is here. So it's just defined as the size, call n, right, divided by the size of the array, which is m. So just n over m, or size over m. When alpha is 1, then that means the table is 100% full. But that may not mean that every array entry is occupied. It may not even mean that like you can't add any more new stuff. Like there's one particular organization with chaining, the table can get to be more than 100% full. But this is how we measure how full the table is via this load factor alpha here, and it's just defined as size divided by m. Okay, first we're going to look at chaining, right? So with chaining, we're going to modify the entry structure so that the entries are nodes in a singly linked list here. There's no point in using a doubly linked list here. It doesn't sort of add anything to it there. So that means that each of the array entries becomes the head of the linked list here. So all we're doing is we're adding this to our entry structure here so that the entries become nodes in a linked list here. If we have a collision, then we add a new entry to the front of the list here. We're adding it to the front because adding it to the front is a constant time thing, right? If we wanted to add it to the tail, we don't have tail pointers, so we'd have to walk down the list to find the end of the list there. So the new insert for chaining looks like this. So again, we hash our key and we get the index that it should be at there. And then we look at that particular entry in the table. Now we have a linked list, right? We have a linked list of stuff going down here like this, like that, like that. So we have to loop over the entries and the things here, looking for the thing that has a matching key. If we find a matching key, then we update the value, and we're done. We just return there like that. On the other hand, if we get all the way to the end of the list, right, and we did not find a matching key, then that means the key does not exist here. So then we want to add it as a new entry to the front of the list here, what this code down here at the bottom does. So if you sort of imagine that like we have an existing thing here, right? So this is, oops, I want color. Sure. Give me blue. So index H is a pointer to something there like that, right? So we're going to create a new entry. We're going to put the key into it, put the value into it, and then its next is going to be the old table H, and then we're going to update table H to point to the new entry that we just created. The new entry becomes basically the head of the list there. And this is just like a sort of standard push front. I'm just doing it in a one-line way here to save a little bit of space on the slide. The new entries are added to the front of the list because that's the fastest place to add them. One thing to sort of notice here, let me clean this up a little bit here. Give me an erase here like this, right? Give me a bigger eraser, big eraser. Right. What happens if the list is empty to begin with, right? So if the list is empty to begin with, then this is a null pointer, which means that the loop condition is false at the very beginning. So we skip the loop entirely and we just jump straight down here. And again, this is going to be a null pointer. We're just going to create the very first node like that right there. So like this also handles the case where there's nothing in this particular entry. The list is empty and we add the very first node to it there. That's just mentioning that. Again, like exists and lookup, like kind of do a similar sort of thing. They sort of search through the list at that particular spot, looking for a matching key there. Now, assuming that we wrote a good hash function, remember that a good hash function has a uniform distribution here. So after we've inserted n many different sort of key pair values, we have a size of n here, the average length of these linked lists will be n over m. Right? If we have a uniform distribution, then all of those different n things will be sort of spread evenly over the table. So the average length will be n over m, which is exactly the definition of alpha here. If the average length is n over m, then that is the number of times that the while loop here needs to run. That means that insert and the associated things runs in big O of alpha time here. As the table sort of fills up, insert and lookup and exists become slower because they have to loop down the length of those lists there like that. So here's an example of inserting some stuff using chaining. So I'm going to assume that we have an m equals 11, and we're going to use remainder hashing with chaining for collision handling here. So these values here, I'm basically just going to take them modulo 11 and then see where they should end up here. So 45 mod 11 is 1, so 45 goes in index 1. 12 mod 11 is also 1. So we're going to put the 12 at the front of the list here. 12 gets inserted in index 1 before 45. Then we insert 24. 24 mod 11 is 2, so that goes at index 2. Then we insert 73. 73 mod 11 is 7, that goes at index 7. 59 mod 11 is 4, so that goes at index 4. 29 mod 11 is also 7. So again, we insert 29 for the 73 that was already there. And then finally, 36 mod 11 is 3. So that gets placed at index 3 there. When we're done, we have a load factor of 7 because we have 1, 2, 3, 4, 5, 6, 7 things that we inserted. Our size is 7, right? Divided by m, which is 11. So that's about like 0.63. But note that the load factor is based on the number of things in total and not the number of array entries that we use here. We're only using 1, 2, 3, 4, 5 array entries here, but our sort of like, numerator up here, our size is 7. Our size is the total number of things. 1, 2, 3, 4, 5, 6, 7. We're not just counting like non-null array entries. We're actually going through the list and sort of counting how many things are in the list there like that when we compute the load factor here. With chaining, because we're working with linked lists, right, the table never really becomes completely full in the sense of, okay, you can't add any more stuff. We can have a load factor greater than 1, and the table will still like work, but it'll get slower and slower. Usually when our load factor is above 0.5, we should think about rehashing the table. So that means we're going to pick a new m, call it m prime, which is roughly, twice as big as the old m, and then we have to like rehash and reinsert all the key values into the new table here. We have to rehash everything because m has changed, which means like where they will end up has a sort of change there. This is something you do, like it doesn't matter what collision handling you're doing here, right? This is not just for chaining. Rehashing is just a general thing that has to be done when the table gets too full. The other option is called open addressing. Again, the idea behind open addressing is if the entry you want is already in use, look somewhere else. Now, your second choice, that might be in use, so we might have to look somewhere else again and so forth. So here, our search is going to look something like this. So we're going to hash our key, and we're going to call that H0. Like that's the spot where ideally it ought to be there. And then H is initially H0, but that's going to change here. I is keeping track of basically how many attempts have we made to find an open spot here. So initially it's 0. I haven't made any attempts. But every time we sort of check a spot and we're like, nah, that spot's full, we will increment I. So as long as entry H is not a null pointer and the keys do not match, right? So that means we have a collision here. We're going to look somewhere else. So we're not actually writing like a look somewhere else function. I'm just sort of using that as a placeholder for how do we look somewhere else? Like what's the process by which we look somewhere else? And that is based on the sort of initial hash as well as how many attempts we've made here like that. We take our sort of original hash value and the number of tries that we've done, and from that we compute some new place that we want to look there. And eventually, hopefully, we find either a free entry or a matching entry where the keys match there. And then at that point, we move on with the rest of the stuff there. So there are 3 different ways that we can kind of like look somewhere else here. The simplest is linear probing. And that just is, if the entry you want is taken, check the next entry. And if that one's taken, you check the next entry after it there. If you reach the bottom of the table, you wrap back around to index 0. So you could define this like look somewhere else here as just the starting hash, H0, plus I modulo M. The modulo M just causes it to like wrap back around to 0 if it goes off the bottom of the table there. So that's the simplest one to define, but it has some like problems when you sort of do it in practice here. A little bit more complicated, but a little bit like better is called quadratic probing here. So this uses a sort of quadratic equation to scatter the sort of like search pattern through the table here. So we're going to define our sort of search pattern as the initial hash plus a constant a times I plus another constant b times I squared. And again, all of that is modulo M, which just makes it wrap back around if it goes off the bottom of the table. And A and B are constants. They don't have to be integers. They can be fractions. But of course, we don't want B to be 0. If B is 0, then this basically just devolves into a version of the linear probing here, like that. The most sophisticated way to do this is called double hashing, where we have 2 hash functions. We're going to use a secondary hash function that we'll call hash2 here, mix up the pattern even further. We take our base hash value H0, and then to it we add I times our secondary hash value there. So that way, as I increases, we sort of search in like different weird places in the table there, but it's different for each key because key gets a different secondary hash value. I'll give you an example of linear probing. The other 2 are kind of like, a little bit involved to kind of like work through there, but you should kind of know like, the basics of how they work here. Let's try linear probing. So this is the same set of values as before and the same size, m equals 11, but we're going to use open addressing with linear probing here. So 45 mod 11 is 1, so 45 goes at index 1. 12 mod 11 is also 1, but 1 is in use. So there's no linked list here. What happens is 12 gets bumped to index 2. Like again, with linear probing, it's just if the spot you want is in use, check the next spot. 24 mod 11 is 2, but 2 is in use. So 24 gets bumped down to the next spot. So this one's a little bit weird, right? Because 24 doesn't naturally collide with any of the other values here. Nothing else hashes to 2. But because there's something in spot 2 that shouldn't be here, 24 is kind of like a secondary collision, right? It's a sort of like artifact of the probing scheme here. 73 mod 11 is 7, so that goes at index 7. 59 mod 11 is 4, so that goes at index 4. 29 mod 11 is also 7, but 7 is occupied, so 29 gets bumped index 8. And then finally 36 mod 11 is 3, but the 3 is occupied, so 36 gets bumped 2 spots down here. It has to search all the way down to index 5 to find a free spot. So this set of keys, only 2 of the keys here sort of naturally collide, right? 12 and 45 collide, and 36 and 73 collide. So we only have sort of 2 natural collisions. That's what we sort of saw when we did the chaining here. But here we have 4 collisions because the linear probing puts things where they don't belong, right? So we run into more collisions than we would sort of expect if we were just looking at the values sort of as is there. Linear probing suffers from a problem called primary clustering, which is where the keys sort of hash into the same part of the table, and then they get pushed down, and then that forces future keys to get pushed down even further. And so it just sort of like, as the cluster grows, the performance degrades because we have to search further and further and further to find an empty spot there like that. Quadratic probing tries to like sort of solve that by introducing this I squared term here. So as I increases, we search further and further away from our sort of starting point there like that. You choose these constants A and B based on sort of M. So if M is prime, you can kind of choose anything for A and B here, at least up until the table becomes kind of half full. And as we mentioned, if the table is half full, you should be looking at rehashing anyway there. If your M is a power of 2, then it actually works for A and B to be 1/2. And that guarantees that we sort of like won't miss any of the table elements. Like we can hit everything from 0 to M-1 there. Quadratic probing solves the primary clustering problem, but it suffers from secondary clustering. So instead of a few big clusters, we get like lots of little ones here. The performance impact isn't as bad though. Like I think the Google C++ standard library, which is called ABSIL, I think that's how it's pronounced, uses quadratic probing. So it's like, good enough to use in like a sort of real world, like, scaling sort of code base there. The last one is double hashing here. So here we have another hash function, which has to be completely independent of our sort of main hash function here. They have to be like totally different things here. We take our initial hash value, and then to it we add I times this secondary hash here. So each key gets a sort of different search pattern because each key gets a different secondary hash there. This eliminates clustering entirely. Like this basically looks essentially like a random search pattern here. But in practice, it kind of like gives us lower performance because modern CPUs are kind of optimized for like predictable search patterns here. And this search pattern is just like totally unpredictable there. So it's kind of like theoretically the best, but in practice, like maybe it's not as good as like sort of quadratic probing, or even linear probing can outperform double hashing in certain circumstances. Now, if we're using chaining, removing things from the hash table is easy. You just go through the linked list and then delete the node when you find it here. With open addressing, removing things is a little bit more sort of subtle here. So let's say we're doing like open addressing with linear probing, right? So we're just being like, all right, where should this go? Here, no, that spot's taken. How about here? No, that spot's taken. How about here? No, this spot's taken. Oh, here's an empty spot. We'll put it there, right? So then let's say that we remove one of these things, right? So we delete the thing that is there, leaving that spot empty. If we go looking for this thing later, we're going to be like, is it here? No. Oh, here's an empty spot. Well, it should be here, right? Because if there's an empty spot, we would have put it there. Since it's not here, that must mean it does not exist. We don't even continue our search to find the thing sort of down there like that. So we're going to stop our sort of search too early unless we're careful. So what we do is we use this thing called tombstones here. So this is an example of that sort of problem made a little bit more concrete here. So let's say that we insert 1, 11, and 21 into a table of size 10. So those will all hash to 1. So the 1 will go here, the 11 will be pushed down to here, and then the 21 will be pushed down sort of 2 levels there like that. So if I insert those 3 values, this is what we'll have. Then let's say we remove the 11, leaving this entry as a null pointer. Right? So now we go and we look for 21. So we're like, okay, 21 should be here, but it's not. E doesn't match, so we check the next spot. If this is now a null pointer, we're going to be like, well, 21 should be here, right? Like this is an available spot. The rule for linear probing is use the next available spot. So if 21 was in the table, it would be here at index 2, but there's nothing here, so therefore 21 does not exist. We don't even sort of continue to look in this spot here because why would we, right? Like why would I look beyond an empty spot there? Like, so what we do in open addressing is we use a tombstone to mark removed entries here. So instead of setting them to null pointer, we just set them to this special sort of entry here. Like it's just some unique entry that means this spot used to be in use. So that way, when we do a search for something, we know, oh, there used to be something here. I should continue searching beyond this spot here. When we compute the load factor, we have to include the number of tombstones in that sort of like count for the number of in-use entries here, because we want to get the true size of the table here like that. Otherwise, we'll be underestimating how much of the table is available for us to use there. All right, to sort of sum it up, right? Hash tables implement a generalized array. The keys can be basically anything there. The runtime of inserting and looking up values is O of n in the size of the key, because our hash function has to loop over the characters in the key, but it's O of 1 in the size of the table. It doesn't depend on the number of things that we've inserted into the table here. Unlike a binary search tree here, we don't require the keys to support ordering, so they don't have to be something that we can like compare with like less than, equal to, or greater than there. But on the other hand, if you sort of look through the table array, you won't find the keys in any particular order there. So that's a hash table there. In C++, if you do hashtag include map, you get a balanced binary search tree, which means that the operation take log of n time, and they have to support comparisons. They have to support less than, equal to, and greater than. Whereas if you hashtag include unordered map, I can spell, then you get a hash table. So it does not require ordering. It's an unordered map. But on the other hand, unlike a binary search tree, you can't get the things out in any particular. So that's a hash table there. That is the sort of end of module 5 there like that. This week is kind of weird because it's sort of split between module 5 and module 6. So if you want, you can move on to the video about binary heaps, which are the first thing in module 6. Or you can take a little breather and go get yourself a snack and drink. Bye, everybody.